Hello, everyone. My name is Kelly Hall, and I'm a marketing coordinator here for ALS North America. I want to thank you all for joining us today for our webinar Wednesday. Our presenter today is Ellingson. Julie graduated with a Bachelor's of Science from Montana State University. She started with ALS as a radiochemistry instrument analyst in 2000, and during this time, she became proficient with analyses using gas flow proportional counter, liquid scintillation, and alpha spectroscopy and gamma spectroscopy. Yeah. In time, Julie became a project manager where she assisted clients during the initial setup phase of project planning by coordinating the analytical tests to meet the regulatory and project requirements. Now, Julie serves as the laboratory director of ALS Fort Collins. Her commitment to client service, combined with her technical expertise and experience, make her a valued partner for ALS clients. And today, Julie will be discussing what TENORM and the analytical options available. During this presentation, please use your chat box or ask a question or raise your hand features to ask any questions. Julie, thank you again for taking your time to deliver this presentation, and I will go ahead and turn it over to you.
Hello, everyone. So thank you again for joining us. I'll be discussing what TENORM is. So to really understand that, we first have to discuss what NORM is, naturally occurring radioactive material. It's material that occurs naturally. It's not byproducts of anything or special nuclear material. It's there in the world. It's the soil, the water, and it's undisturbed by human activity. NORM is everywhere. It's a part of our daily lives. It's in the earth we stand on. It's in the air we breathe. It's in our food. So we're always surrounded by some levels of radiation. When we get to TENORM, which is technologically enhanced naturally occurring radioactive material, that's where we've done something to it. It's been concentrated by a result of something in our process we're doing. So it's usually a byproduct of some sort. So there's a number of places that TENORM materials are typically found. You're going to have things like pipe scale. Deposits are going to be concentrated in pipes as the hard water settles in there. Tank bottoms, again, wastewater treatment, sediment ponds, reclaimed drilling muds, recycled fracking water, scrap metal, filtrates, whether it be liquid or solid. All of this stuff is things that have gone through a process that had naturally occurring radioactive material that has gone through there. And then due to some form, it's now in a larger quantity than what it would be in a natural form. So there are certain level of radionuclides that are typically what we're going to be talking about. Mostly it's the uranium and thorium decay chains, as well as radionuclides such as K40. K40 is actually one that you will see a lot out there. Typically not the one that most people are concerned about, though. I have listed here the uranium decay chains and the thorium decay chains. The darker highlighted ones are typically what the isotopes that people are going to analyze for when they're looking for thorium or for TENORM products. The other nuclides typically have too short of half-lives, so they're not around long enough for us to really see. Also, usually, you're going to start off towards the top of the decay chain most of the time because that's where your daughter products are. All of these things can also depend on what process it's from. So if you're doing something like pipe scale, some of the things that tends out, that's where you're going to see something more like the lead-210 and be concerned at that point. So when testing for TENORM, there are a number of different analytical methods out there that are available to use. And this is just a listing of the common methods. Some of these have more. You're going to see stuff for gamma emitters. You'll hear things for the EPA 900, or 901.1, Hassel 300. For radium-226, there's quite a few out there. Again, you can use it, can be seen by gamma, or it can be done by 903, 903.1, SW 846 methods, 9315. You can run it by alpha 904, 9320, thoriums and uraniums have a couple different methods there. So these are just your common methods, the most common ones you're going to see out there. There are still a number, sometimes state things that will be out there for methods. When considering what method you need, there are a couple things to think about. I mean, what isotope are you looking for? Are you looking for a very specific target, like I need specifically this uranium, or like I need a broad search? If you're looking for a broad one, gamma spectroscopy, where you can get a lot of different targets in at one time. If you're looking for specifically lead-210, you can go with another method for it. The detection levels. Not all methods get the same level of detection. So if you're looking for very low levels, high levels, or somewhere in the middle, depending on what you need, can help dictate what method you should be running your analysis by. What is your sample matrix? Soils, water. You get the others because you have filter socks out there, air filters, stuff that usually is a solid but is definitely not soil. What method works for it? Some methods will work better on a solid, some won't work at all in a water, so you need to know and discuss what it is for that. And then how fast do you need the results? Many of these tests have time constraints, especially when you're discussing the radium-226 methods. Some of them, if you're doing it by gamma, there's one method that requires a 21-day ingrowth time, a waiting time that you have in there. So if you need the results faster, there's other methods you can use and other ways of looking at it. Again, are there specific regulatory requirements you need to follow? Are you doing this for a permit? Are you doing this for a specific state that has said you need something? You'll need to convey that very well. Don't assume the lab will know. Many times they're not going to know all the parameters of what is needed for you to test for this. And just on some of the methods to go through for it, you know, that we had brought up earlier, you have gamma. This one gives you a broad range. Depending on what it is, you kind of have higher detection limits for this method, especially for waters. You can get a very fast turnaround time on this, except you're doing a lead-210 and bismuth, or lead and bismuth ingrowth daughter products for radium-226. If you're using that direction of it, it does take a 21-day ingrowth. So there's other ways of doing radium-226 by gamma. You can do it with no ingrowth, or you can use a direct count. There's high biases and problems to that. So it's always good to discuss what you need for it. Radium-226 by the gas flow proportional counter is typically your 903 and your 9315. There's also some standard methodologies for it. It's really good for waters, doesn't work very well for soils. There's a lot more interferences that happen there that can cause problems. This is actually also meant to be a screening method for total alpha emitting radium. So usually if you want to try to target radium-226, again, there's a time constraint in there where it's going to have approximately a 14-day period typically used in there. So you can switch over and do it by the 903.1 method, which is by radon emanation, or you can say alpha scintillation. It's a definitive. It works well for both waters and soils. There is a little bit of time constraint there. We do have some ingrowth time period. We do anywhere from 4 days up to 14 days. So it depends on what you need for that. And your detection limits are pretty good for both of those. But if you really need low detection limits, you can go and do radium-226 by alpha spectroscopy. Then you get to the radium-228. That one is by gas flow proportional, 904, 9020 are the methods. It does well for waters, but it's not good for soils. If you do soils, you should go back to the gamma method. Now, one of the things you'll see a lot of commons when people are looking for stuff with NORM and TENORM is that they'll have radium-226, radium-228 combined. It is always good to know that those are two separate compounds you're not going to get typically one analysis that's going to give you both result or a combined result. Typically, especially in waters, you're going to have to run the 226 by one of the methods and the radium 228 by the 904 or 9020, and then the result has to be mathematically combined to give you a combined result. If you do see something that says total radium, that's usually referring back to the total alpha radium, which is 903.0, and that does not include radium 228 because it's actually in a different decay chain, those two, so they're a little bit different. Isotopic thorium, isotopic uranium, you can get a lot of the uraniums and the thorium products by gamma, but again, if you want lower detection limits, the way to go for that is by alpha spec. So there's a lot of different choices out there to use on what you're testing for. Sometimes you don't need thorium, you don't need uranium because you know what your product started with. Maybe you're only looking for the radiums because that is what you know is there. So it's good to know what your method is by knowing what you're looking for. So on regulatory requirements, NORM and TENORM aren't regulated by the NRC, which regulates most of your other radioactive nuclear materials, but they don't have jurisdiction. They don't take anything over NORM and TENORM. The EPA doesn't really have anything out there for NORM. There's a little bit of stuff they have saying about TENORM, but it doesn't go into very large directions. So what this has ended up falling into is that this regulation of TENORM is not consistent from industry to industry, or even from state to state, or I've seen it within sometimes certain counties within the state have slightly different things than what the state has. There are a number of states that have some sort of form of regulations, or in some cases I refer to it as guidance documents because they won't put a regulation out because the EPA doesn't have something set. So they'll put a guidance document out. And they can be different from every state, which is why we want to say you need to make sure you know what your state is doing and what your regulations on that before you ask the lab to just, I need TENORM, because it can mean something different from place to place. Even for disposal purposes within landfills have their own requirements of what they're allowed to do, so they can dictate specific isotopes that they need to have tested for, and sometimes will tell you, hey, I want it by this specific method. So you need to verify those requirements with the landfill before submitting the samples to the laboratory. If you submit samples in and then find out, oh, I needed this other method, or these aren't the right isotopes, you might not have sent the right volume. It's going to cost you more time and more money because you're going to have to usually get started after the fact, which is never a good thing. The
Julie,
last little bit.
we
Yes.
do have a one question and as well as a hand raised. Do you have a moment?
Oh, yeah.
Okay, perfect. So the first question was from Gary. He asked, where does depleted uranium fit into the NORM TENORM scheme? I believe you were on slide 4 or 5.
So most of the time, depleted uranium, when they get to it, they're usually going to look at that depending on what levels it actually steps outside of the norm rate or TENORM and can fall under the regulations of the, let me get to it. So it can actually end up falling under some of the other regulations at that point for special special material and stuff, depending on what it is. So it depends on the levels of what the uranium is at, which again is kind of weird because if you don't know beforehand, how do you know where it falls in until after you have your analysis? Very rarely do we see a full amount of depleted uranium from any place that isn't a nuclear facility though. So usually we don't see much. You just see the natural ratios with NORM. Once it falls out of that, they don't really consider it in a TENORM business. Did you have anything else there, Kelly?
Yes, ma'am. I did have one from Walter. He asks, what about OSHA regulations?
Now, OSHA regulations get to the point where they're again looking at a health risk, and they're still filling their way on some of those. So there isn't as many out there that I am super familiar with at this moment. So usually uranium has a few things out there, and the radon does, but I do not know what all of their requirements is. Most for testing purposes, when you get to, we'll go back here really quick on that. So radon is what you're going to hear about the most in an OSHA setting typically, because it is gas, it's breathable. There are ways to test for that. It has a very short half-life. The other thing it does go into, what it decays into, is the leads. Most of these are very short-lived until you get to the lead-210. And those are, again, heavy metals. So you can do air filtrations to get your particulates and be able to test to see what levels of lead-210 is out there. So there are ways of testing it for the source material, which is radium-226, versus going down to the daughter product of lead-210. Even for uranium, if you're in an area that has it, those can also be tested. We are set up here to do the NIOSH 7300 for uranium if needed for a number of places. So that is the only one that has an actual OSHA method. None of the other radionuclides really, they tend to still then default back over into your EPA methodologies. There hasn't been anything set up specifically in OSHA for a test for radionuclides for most of these things.
Those are all the questions we have at this time.
All right, well, basically I just did this as a quick overview. So one of the last things I was just going to say was kind of how change of our view on radiation and stuff has been over the years. Because when radium was discovered in the early 1900s, they actually had these devices which they would call invigorators. And it's a crock lined with ore that had the uranium and radium in it. And it would go into the decay product of radon, which would infuse the water, and then you were encouraged to drink the water the next day to invigorate your health by having this, which is kind of an interesting thing nowadays where radon, I live in an area here where in Colorado that we have a lot of places that have radon mitigation systems within their basements because we have radon, you know, testing people's water for the radon because we can dissolve that and stuff. And you don't want it there because we know that's the second leading cause of lung cancer and such. So a lot of these things used to be out there, and we used things for these natural radiations for health products, and nowadays we're all concerned about what we need to do for it. So it's an interesting thing. So, but that was basically it. This was an overview. I do encourage you, if you have direct questions on the different methods, radium is one of the ones that is probably the most complicated because there are so many choices out there and options. But again, the part that is good to say, what do I need? If you ask these main questions here, you can get a good help and discuss things with whichever laboratory you want to work with, and they'll be able to help you figure out what method will work the best between you guys. So we always want to be able to help you and give you results that will meet your needs. So unless there's anything else,
Yes, we do have a
that is
few
all I have.
questions coming in, Julie. Thank you so much for your presentation. As questions do come in, feel free to either use the raise your hand feature, I can unmute you, or just write your question in the question box and I will go ahead and answer them and send Julie your questions right now. So another question we have is from Kathy in Texas. She said, a real world situation. ALS helped us out with the TxDOT roadway issues with NORM in West Texas. Is there a database of the data? For example, you have average norms.
We don't have that, but there are databases out there. The USGS actually has a number of places where they've done studies throughout the U.S. and so each region they can tell you approximately where your background levels are. I happen to know some of the stuff more directly for Colorado, but I don't know all over the place. But that's usually your best bet, is to look through for things. I know the USGS has a really good one, and I do believe there's a few other places. The EPA might also have something out there too.
Okay, and another question's from Carl. He says, can you detect daughter products but not parent products in a norm sample? He does give examples if you do need those.
So I might want the examples, but just to start off with, so we can do the daughter products without the parent product. Sometimes what it does is it ends up becoming a assumption based on secular equilibrium based on different nuclides. So especially usually if you're doing stuff within gamma, many of those things you're going to, someone says, hey, I need to know what the thorium-234 is, or most of the time when you're analyzing radium-228, we're actually going to take actinium-228 is what we're counting, and we're going to make an assumption that based on this time frame and everything, it's equal to what it is before. So the problem comes when we start doing things in TENORM, because depending on what the process is, that's where you could have broken the decay chain. So while we can do the daughter product, sometimes we can't infer back to the parent product just because of the fact that the decay chain could be broken, and what you're getting based on solubility issues and everything else don't match up correctly anymore from what it would be in a natural environment. So what were the examples, Kelly?
Sure. The daughter products is that example TH228, TH230, RD226, PB210, and the parent products were examples TH232, U238.
And stuff. So on most of those, we're going to do through our gamma, where we're going to be looking at a number of the smaller daughter products. And I didn't write them down, so there's a lot of numbers there, and I can't remember all the isotopes you had listed. So
there were a lot. If Carl, if you did want to follow up, feel free to raise your hand, and I can unmute you if you want a direct question. And we will go to the next one. Jay asks, will you please provide a quick overview of reading data?
Of reading?
That is what it says. Yes, ma'am.
All right, so most data for RADCAM, for radionuclides, are given to you in activity basis with what we call the uncertainty, the TPU, total propagated uncertainty. So most of the time, and then an MDC. So you're usually going to see your result looking like, as an example, 3 plus or minus 2 MDC of 1. So there are different ways of looking at the data. Some people, we can look at it strictly off of the MDC, which is our minimal detectable concentration. So R3 is greater than the MDC of 1, so it's a hit. Some people will then take it and say, oh, I know your uncertainty bar, so we're going to say, well, 3 minus 2 is 1, which is the same as the detection limit, so is that really a hit or not? And that becomes a question there. Although if you're doing it that way, it's just as equal to say then 3 plus 2 equals 5. So you're somewhere in that range. Some places look strictly at just what the TPU is and not looking at the MDC, but so it gets a little a little bit differences in there, but the majority of people tend to look at it as what's the concentration, what's your activity, and then you can look at what your uncertainty bar is for it. Every time we count a sample, we can reprocess the same, prep it, count it. I can turn around, count it again tomorrow, and I will get a slightly different result. How it works for this is very much a statistical number versus a hard and fast. This is what it is. So that's how come every time you're going to get a slightly different MDC, you're going to get a slightly different result, but they should be all well within a reproducibility range.
Thank you. I have another question from David. He does have his hand raised, so I am going to unmute him in case he would like to speak. David, did you have a question to ask Julie?
Go back to worksheet A.
Okay. He does have a written question. He says, are there methods to detect other radionuclides, Americum-241, Curium-244, and Neptunium-237?
So yes, so the americium, curium, and neptunium are all done by an alpha spec methods. They all can fit within ASTM method or kind of fall in with the Hassel 300 for both of those. You will see both of them are very similar for, in most cases, the americium, the neptunium, and the curium typically are more considered fission products versus natural, so you're not going to really come across them in a natural setting. But we do test for them here, and they're going to be very similar to what we use for uranium and thorium methods.
Thank you. I have another question from Barbara. She said, I have seen results from different labs, each analyzing for PB210 and PO210. From one lab, the results from PB210 and PO210 are identical. From another lab, they are different. Why?
So actually, I find it more interesting that you could have gotten something that was identical versus different. I'd be curious to know how different. So when comparing results from one lab to another, even if it's the same thing, double check to see if they're using the same method, what type of instrumentation they're using. The lead-210, if they're using liquid scintillation, are they going down to a lower detection limit, or are they not able to see as low? The polonium, again, it's the same thing, depending on what levels they're looking at, what is their method they're using, because honestly, it can be, if they're using slightly different methods, they might have, different interferences or something else that's there that they're not getting as good of a reading as one of the others. So it gets a little tricky sometimes to say comparing one lab's work to another unless they're using hopefully the same instrumentation, the same prep methodologies and such like that, because it can be different. One thing I will say about both polonium and lead is, especially if it's a solid, if you had someplace that did anything with high heat for those, both of those can actually be volatile at certain levels of temperatures. So if they did something that they heated it up in the process, it could have lost stuff on there. So.
Thank you, Julie. That is our last question. I don't see anything else coming through. So I just want to say thank you to Julie for this presentation today, and thank you to everyone for attending this webinar. This has been recorded, and we will post this on our YouTube channel. Just search ALS Limited to find our channel, and then click on the North America playlist. There you will find a wide range of our video resources and past webinar Wednesday presentations. Also, please follow our showcase page on LinkedIn, as well as other various forms of social media. We will post links to future webinars and other valuable resources there. Thank you again for attending, and it looks like there is one more question from Kathy. She actually wanted to follow back up with you with a phone number, so I will go ahead and pass that on to you, Julie, after this webinar. And again, thank you everyone for attending.